Hi, welcome to another lecture on Calculus 3. Today we are going to continue our conversation about iterated integrals and area in the plane. We are going to finish a certain set of problems we started last time, and hopefully we'll have a little demo to make sense of the algebra that we are doing. So let's go back to this set of problems. We did A, B1, B2, B3. Going to do B4 and C now. So this problem B4. As you remember, the question was to exchange the order of integration and sketch the region on which the integration is being done. The particulars of f of x and y do not concern us right now. We're just understanding what the limits means. What we are going to do is we are going to draw the coordinate system. Detect what is the first sweep that we are doing. We are doing it in the x direction. We're doing in the x direction starting at x equal to 0. So from x equal to 0 to x is equal to logarithm of y. Let's have a picture of what these things mean. X equal to 0, well, it's easy. That's just the y-axis. X equal to logarithm of y. Perhaps it might be more familiar to us if we exponentiate both sides. It becomes exponential of x is equal to y. We normally write it y is equal to exponential of x. So these two limits, one of them is just this is where more or less where we are starting, and the other one, y equal to exponential of x. Well, let's say this is 1. So exponential of x is a curve that goes up like this. So y is equal to exponential of x, or x is equal to logarithm of y. These are same thing. So we are starting from here and going all the way there. So if I pick a particular y to start at, I start stretching from x equal to 0. So this is x equal to 0. I go as far as x is equal to logarithm of y. Once that is done, my y, the second sweep, goes from 1 to 10. Where is 1? Well, exponential of 0 turns out to be 1. That's where we start. And let's say 10 is somewhere here. So the region of integration becomes this triangular looking region. Well, of course, this is a curve here, and the entire region we are sweeping is going to be this. So this is the region of integration. We are bounded by these curves which specify this yellow region. Now the question is, what if I want to switch order of integration, meaning I want to go y first then x? Well, if I want to sweep in the y direction, I'll be going vertically up. So this is going to be the strips I'm picking out at that time. First of it, this type of strips all the way here, and the last of it is all the way there. So when we go in the vertical direction, y goes from, well, we start with the location x. Our starting location has to be given in terms of this. It goes from exponential of x to our stopping place is 10. Once that is done, x is going to go from, well, the first strip is this one. That is, of course, from x equal to 0. The last strip is here. Well, what is that? We said equation of this curve is x equal to logarithm of y. If you have 10 here, this is going to be x is equal to logarithm of 10. The last place we are sweeping is logarithm of 10 here, so this is going to be x is equal to logarithm of 10. So my integral, double integral in the interior from this location to this location is same as e to the x to 10 of f of x and y. Y goes first now, last goes x. X goes from 0, start at 0, and the highest is logarithm of 10. Okay, so that is the conversion. You want to make sure you do this several times by yourself. Better yet, there are many problems of this type at the end of this section. You want to do large number of these to become comfortable with what's happening. So last problem we are going to do, we are going to put this idea to good use, which is the following. We have an integral there, interesting integral. It goes like integral from 0 to 2, integral from x to 2 again, of x radical 1 plus y cubed. Whole thing, the y is first, of course, and the x. Question here, simply evaluate the integral. Okay, what is the challenge? The challenge is this: the way this is written, the integration has to be done versus y first. The very first thing is the following. Well, that turns out to be quite a challenge. In fact, none of the things we have learned in an entire calculus sequence is going to help us do this thing easily. None of our functions match it. In fact, it turns to be somewhat a new function, sometimes referred to as a hypergeometric series. Either we have to do expansion and integration and such. Any which way we want to try to do this thing is not going to be easy. But if we try to switch the order of integration, just like what we have done in any of these problems, that problem turns into a trivial problem from Calculus 1. So this is worthy of an entire new course all by itself, perhaps an advanced version of differential equation or something. But if we switch the integral, it becomes a trivial thing from Calculus 1. So that's rather surprising that something like this happens. So to switch, well, first we need to know what's happening. We need to know the region of integration. So it's y going from x to 2. So at the bottom is y equal to x. So I draw y equal to x. This is at the bottom. At the top is 2. So let's suppose this is 2. And then x ranges from 0 to 2. So this is 0, and of course this is 2 again. So the region of integration is the following. And the manner of integration here is go vertical first, and then x ranges from 0 to 2. We just try our luck at going the other way, that is going x direction first. X direction first, and again I'm going from this 0 to this 2. So the other one is this 0 to that 2, but when you go switch them, it's going to be this 0 to that 2. So we are going to write this thing. When we switch it and we want to go in the horizontal, well, x starts at what? X starts at 0. Where does it end? At the given y location, my ending location x is just equal to y. So I go as from 0 to y. My function is same as before. That does not change. we are saying x goes from 0 to y, and then when y is to be taken care of, y goes from 0 to 2. So accidentally this looks like that, but they means different arrangement. Okay, so far we have just switched x and y. I mean, exchange the order of x and y. Now we look at this interior integral. I'm integrating with respect to x. Y is a constant. So what does that give me? That's going to give me x squared over 2 radical 1 plus y cubed. So integral is easy. This is a constant. This integral then is to be evaluated between 0 and y. What does that mean? We said this y is limit of value of x. Once that substitution is done, the last integral is to be done from 0 to 2 of dy. Well, 0 to 2, if I substitute y for x, this becomes y squared radical 1 plus y cubed, and then I have a factor of 2 and dy. Okay, so this has to look very familiar to you from calculus 1. Pause this thing for a second. So let's insist on students doing these things themselves. Do that integral. So it has to, you should be able to do that in a matter of couple of minutes at most. How do we start? Well, let's do a u sub. U, my integrand. Why is that a good idea? Because du is 3y squared dy. Therefore, y squared dy can be substituted. But du third. Let's also switch our limits of integration. When y is equal to 0, of course, my u is 1. And when y is 2, my u becomes 9. So that integral, now we are ready to do wholesale substitution. We're going from 1 to 9. In u language, we're going from 1 to 9. U squared dy is going to be du third. I have a factor of 1/2, and this is a radical u. Okay, now let's clean this up. I write it as 1/6 of integral from 1 to 9 of u to power of 1/2 du. And that is 1/6 of antiderivative is u to power of 3/2 over 3/2 from 1 to 9, and 6 times 3/2 is going to be 9. 9 to power of 3/2 minus 1 to power of 3/2. 9 to power of 3/2 27, minus 1 is 26, and it looks like our answer is 26/9. That is what this integral is. Again, the emphasis is this will take several weeks to do it based on the knowledge we have right now, and so we did the whole thing in just a few minutes by using tools from calculus 1. Okay, so we have learned a little bit about iterated integrals. Now let's go ahead and get a visual understanding of what this thing is, and to make the issue simple for us, let's just go after something with the limits of the integral, perhaps all of these things being constant. What does that do for us? At least simplifies one aspect of this. So y ranges from c to d, so wherever c is to wherever the d is, the y ranges between these two. And x ranges from a to b, so wherever a is and wherever b is, that's going to be the range of x value. So the domain that we are integrating is a rectangle. So at least that portion of the problem, let's simplify that. So the base is just a rectangle. What does this mean? what it means is very similar to the Riemann integral we had in Calculus 1, which is the following. You take this region and divide it to some cells. Now in each of these cells, so you pick one cell here, you say, well, what's the value of f of x and y in that cell? You have a particular x and y, you are in a certain vicinity, so you can calculate f of x and y, say, at the center of this cell. And then how can we make sense of dx dy? Dx dy is like this is going to be width of these cells is dx and the height of these cells is dy. So if you multiply dx times dy, this is the element of area. Sometimes we show it by dA, element of area. What is f of x and y? F of x and y is going to be the height of some function at this point. So I have here whatever this thing is some sort of a height. So what is height times the area of base? If you have a base and then on top of that you build something, well, what do you make? Of course, that is just a box. Height times, so down here we have area of the base, and here we have the height. If you multiply base by height, what are you calculating is an element of volume. So we might write this thing as element of volume, and suggestively the element of area times the height becomes the element of the volume. So what we are doing is adding up volumes of boxes that are having different heights on different cells. Just the integration simply means add up all those little pieces of volume. Let's go ahead and look at it in a Geogebra app, so hopefully the problem becomes more understandable. So let's hope that this thing works. Takes a while for it to load. Let's make thanks to Joseph Manti. So let me make this numbers so that things stand out for us. And okay, so we have some function here. You can go type whatever you want. It's f of x and y, some function. This is a nice paraboloid. And then we have the domain, that rectangle we were talking about. You can define it however you want. For x minimum to x maximum, I'm going from -2.5 to 2.5, y minimum to y maximum. So this is what the rectangle is, from -2.5 to +2.5, from -2 to 2, or whatever you want. Then we make cells. So I am making a grid here, 6 in the x direction, 5 in the vertical direction, just whatever number that pleases you. Now if you go look at this, the bottom of this rectangle, at the bottom of this rectangle you see these cells. This is an exact copy of what you see here. Okay, there are all boxes that are built on top of these rectangles. What's the height of this box? The height is coming from the function. So for example, we go to the center of each cell. It has a coordinate, x and y coordinate. We plug it here, we get a value. This is our z value. Z is the height of the box. So if the height of the box multiplies by the area of the base, what we calculate is the volume of that box. Now on each of these grid points there is a box of slightly different height, so they are all having different volumes. If we add them all up, we have an approximation for our integral, which in this case means the volume underneath this surface. So if you have a surface here that looks like this, the paraboloid, the portion of that surface that is covering this rectangle, well, that thing has a volume. What we are doing by this double integral would be calculating the volume of that. When you make a grid, your result is going to be an approximation. Of course, you can always increase your number of grid points that you have if your computer allows it. Mine is probably going to freeze. It did. So of course, when we have a lot of grid points, our cells are going to be packing next to each other. The approximation gets better. We have lots of little contributions, and when you let the number of grids go to infinity in x and y directions, then you reproduce the exact volume that's at the limiting value. So what we are doing in this case, you can think about it as calculating the volume of a region, that is, so volume under surface z is equal to f of x and y, and over rectangle. So the rectangle, sometimes we write it like this: interval AB times interval CD. That is the rectangle that we have. So that's how to make sense of an iterated integral. Now, if instead of a rectangle we had something else, for example, in this case we had like a half of a rectangle or half of a square or something, still the idea applies that we are calculating the volume of whatever this surface is, and is sitting on top of this particular shape. So in general, if you have a double integral of something, of some function, over or some region, so I could have some region that does not have to look like a rectangle. It can be any region I wish. So if I subdivide this region into little cells and go ahead and calculate the area of this cell, call it dA, take that element of area, multiply by this function which is supposed to play the role of the height. So this is going to be height of the sum function. This is going to be the area of the base, an element of the area of the base. When we multiply these things, we get the element of volume, so then these volume contributions all over the region is going to be added up. That would be the meaning of this particular symbol. So it's important to understand what is aimed by these iterated integrals. Pretty soon what we are going to do is not going to be related to volumes anymore, but to understand what the iterated integral means, this approach helps quite a bit. Okay, so in the next section we are going to look at more advanced versions of the same thing, and more ways of looking at this concept in the context of this app, and see what are practical ways of calculating such iterated integrals. Okay, until next meeting, good luck and God bless.